Welcome to Orbit Observer. It's lovely to have you here tonight, wherever you are right now, whatever corner of the world you've curled up in. I want you to settle in and let your shoulders drop a little. Maybe you're under a blanket, maybe there's a lamp still on across the room, throwing a soft little pool of light across the ceiling. Maybe you're on a train or a couch, or flat on your back in the dark with your eyes already half closed. However you got here, you're welcome. There's no rush at all tonight. And before we drift off into the cold and the quiet, I have a small favor to ask, and it really is small. If you enjoy these slow journeys, if you'd like more nights like this one, a gentle like and a subscribe genuinely helps this sleepy little channel keep going. Small creators like me really do rely on it more than you'd think. And to those of you already subscribed who come back night after night and let me keep watch while you sleep, thank you, truly. So before we go anywhere, I'm curious, where in the world are you watching from tonight? What time is it in your corner of the dark? You can leave it down in the comments if you like, and I'll picture you there, somewhere out across the curve of the planet, getting ready to rest. Now, a small promise, the same one I always make. I'm going to talk slowly tonight, softly. We'll move through this one strange subject the way you'd wander through a quiet house at night, one room at a time, never hurrying. You do not have to follow every word, you really don't. If you drift off somewhere in the middle, that's perfectly fine, that's sort of the whole point. And the ideas will still be here, waiting when you wake. There will be no test in the morning. Nobody's keeping score. So you have my permission right now to stop concentrating any time you like and just let my voice carry on in the background like a tide going out. I'll try not to make this one so interesting that it keeps you awake. Though I'll admit, that's a harder promise to keep than usual tonight. Because the thing we're going to talk about is genuinely one of the strangest objects in the entire solar system. And the more you learn about it, the stranger it gets. But if it does keep you up a little, well, at least you'll have learned something, a fair trade. So here's where we're going tonight. I want to tell you about a planet, a pale, cold, blue-green world, far out at the edge of things, so far away that sunlight reaching it is a faint and watery sort of light, the way a single candle looks from across a very large field. And I want to start with a number that the first time I really sat with it stopped me in my tracks, about 6 hours. That's it. Almost everything humanity knows about this entire planet, a whole world 4 times wider than the Earth, with a family of moons and a system of dark rings and a magnetic field stranger than anything we'd ever seen. Almost everything in the textbook entry for it comes from roughly 6 hours of close observation. One afternoon, really. One single visit by one single spacecraft, decades ago, that swept past it once and then was gone forever into the dark. The planet is Uranus. And we have been there exactly one time. Let that settle for a moment, because it's easy to hear and hard to actually feel. We have orbiters at Mars right now, this very night, circling it round and round, watching its seasons turn. We've landed on it, rolled little robots across its rusty hills for years on end. We've had spacecraft swing around Jupiter again and again, dive between Saturn's rings, sail past Pluto and out beyond it. But Uranus, this enormous, sideways frozen world, we have visited precisely once, a single flyby, and we have never been back. The spacecraft that made that one visit was Voyager 2. You may know the name. It's one of the great travelers, a little machine launched in the late 1970s that just kept going and going past one giant planet after another, a kind of slow, grand tour of the outer solar system. And on the 24th of January 1986, Voyager 2 made its closest approach to Uranus. It came sweeping in and passed about 81,500 kilometers above the planet's cloud tops. That's roughly 50,600 miles, if that lands better for you, high above those pale cyan clouds, close in cosmic terms, but still a long, long way up. And here's the thing about a flyby. It isn't a visit the way you and I might think of a visit. Voyager didn't stop. It couldn't stop. It was moving at tens of thousands of kilometers an hour, a speed that's almost impossible to picture. Faster than any bullet, faster than anything in your daily life by an enormous margin. And it simply could not slow down. There was no braking, no settling into orbit, no staying for a while to watch the weather. It came screaming in out of the dark, took everything it possibly could in the brief window when Uranus filled its instruments, and then it was past and falling away again into the black on the far side, already on its way to the next planet. That window, the close, high-value part, when the planet was near enough to really study, was on the order of about 6 hours. 6 hours, give or take, around that moment of closest approach. After tens of thousands of years of human beings looking up at the night sky, after centuries of careful astronomy, this is what we have for an entire world. One afternoon's worth of close data gathered in a rush by a machine that was already leaving. So everything you've ever read about Uranus, every diagram in a school book, every line in an encyclopedia, every confident sentence about its magnetic field and its radiation belts and the strange, empty space around it, almost all of it traces back to that one brief pass, to those 6 hours on that one day in January 1986. And now I have to tell you the part that turns this from a simple story into a genuinely unsettling one. The part that's the real reason I wanted to talk about Uranus tonight, rather than any of the other worlds out there. Because in 2024, a group of scientists went back, not to the planet, we still haven't managed that. They went back to the data, to those old recordings from Voyager 2, the numbers the spacecraft sent home from that single pass nearly 4 decades ago. They pulled out the original readings from the instruments, the magnetometer that measured the magnetic field, and the detectors that measured the thin soup of particles around the planet. And they looked at them again with fresh eyes and decades more understanding of how these things work. And what they found, I think, is one of the quietly most remarkable findings in planetary science. The study was published in a journal called Nature Astronomy in November of 2024. It was led by a scientist named Jamie Jasinski, who works at NASA's Jet Propulsion Laboratory. That's the place out in California that builds and flies so many of these robotic explorers, the people who, in a very real sense, run the spacecraft that wander the solar system on our behalf. And what Jasinski and the team concluded after going back through all that old Voyager data was this. Voyager 2 arrived at Uranus at the worst possible moment, or, depending on how you look at it, the strangest possible moment. To understand why, I need to give you one new idea gently, and I'll decode it as I go because it's the key that unlocks the whole night. The idea is the solar wind. Now, the sun isn't just a ball of light sitting quietly in the middle of the solar system. It's constantly breathing out, streaming a thin, fast wind of charged particles in every direction, all the time. Think of it almost like a fan that never switches off, blowing a steady, invisible breeze outward across the whole solar system, past all the planets, out into the dark. That breeze is the solar wind. It's faint and it's thin, but it's always there, and it's always pushing. And every planet that has a magnetic field, like Earth does, like Uranus does, sits inside a kind of invisible bubble that its own magnetism blows around it. That bubble has a name. It's called the magnetosphere. You can think of it, if you like, as the planet's own personal weather balloon made of magnetism, a protective region around the planet shaped and held by its magnetic field. And here's the thing about that balloon. It isn't rigid. The solar wind is always blowing against it, pressing on it, and so the size and shape of the magnetosphere depends a great deal on how hard the solar wind happens to be blowing at any given moment. When the wind is gentle, the bubble puffs out, big and round. When the wind picks up, when the sun sends out a stronger gust, the bubble gets squashed, pressed in, compressed. Now, most of the time the solar wind out at Uranus blows at a fairly ordinary strength. The bubble sits at a fairly ordinary size. But every so often, not often, just every so often, the sun lets out a much stronger gust and the wind out there gets dramatically more intense, and the magnetosphere gets squeezed in hard into an unusual, compressed, distorted state. And what Jasinski's team worked out is that this is exactly the kind of moment Voyager 2 flew into. Just days before the spacecraft arrived, an intense burst of solar wind had come through and compressed Uranus's magnetosphere, squashed that magnetic bubble into a state that, according to their analysis, only occurs around 4% of the time. 4%. Sit with that number for a moment, the way I did, 4% of the time. Meaning that if you'd shown up on a random day 96 times out of 100, you'd have found the planet in something like its normal, everyday state. But we didn't show up on a random day. Out of all the possible days in all the possible years, our one and only visit, our 6 hours, landed squarely inside that rare 4% window when the planet was being pressed and distorted by an unusual gust from the sun. We didn't photograph Uranus calm. We didn't catch it on an ordinary afternoon, going about its business the way it does most of the time. We caught it mid-flinch. I keep coming back to that image because I think it's exactly right. Imagine the only photograph that exists of someone, the single picture the whole world has of them, the one in every book, the one everybody studies, and imagine it was taken at the precise instant they sneezed. Eyes screwed shut, face all scrunched up, caught in a strange and fleeting expression that looks nothing like how they actually are, nearly all the time. And then imagine that for 40 years, everyone built their entire understanding of what that person looks like out of that one sneeze, drew conclusions about their character from it, wrote it down as fact. That's roughly where we've been with Uranus, and most of us never even knew. So that's the strange day. That's the catch hiding inside the title. Almost everything we know about this whole enormous world came from one rushed afternoon. And there's now very good reason to think that afternoon caught the planet in an abnormal, transient state, a rare squeeze that had temporarily turned it into something it usually isn't. Now, I want to be careful and honest with you here, the way I always try to be, because it matters. This 2024 study is a strong piece of work, published in a serious peer-reviewed journal, led by a careful scientist at one of the best institutions in the world. But it's also recent. It's a reinterpretation, a new and very compelling way of reading old data. Not yet the kind of thing that's been written into every textbook and settled for good. So the right way to hold it, the honest way, is this. A 2024 study concluded that the Flyby caught Uranus in a rare compressed state, and that this likely distorted part of the picture we've been carrying around ever since. It's the leading new idea. It is not yet final, carved-in-stone truth. And that distinction, so one between what we've measured and what we're now reinterpreting, is going to be one of the gentle threads running through everything tonight. Some of what I tell you about Uranus is rock-solid, confirmed, true no matter what, and some of it may be an artifact of bad timing. Part of the quiet pleasure of tonight is going to be learning slowly which is which. But before we start pulling the picture apart, let me first lay it out the way the textbooks have had it for 40 years. Let me give you the settled story, the tidy, confident picture of Uranus that you'd have found in any encyclopedia. Because to understand what may have been knocked loose, you first have to see what was standing there in the first place. We'll build the calm, familiar version of the planet now, and then, Across the rest of the night, we'll gently take it apart and see what really holds. So, picture the solar system laid out in your mind, the way you might have seen it on a poster on a wall somewhere long ago. The sun in the middle, warm and bright. Then the small rocky worlds close in. Mercury, Venus, our own Earth, Mars. Then a great gap, and the giants, enormous Jupiter, then ringed Saturn. And then, much further out, in the cold and the dimness where the sun is just a very bright star among the others, two more giant worlds. Uranus, and beyond it, Neptune. Uranus is the seventh planet out from the sun. It's big, about 4 times the diameter of the Earth. But it's not big in the way Jupiter is big. It belongs to a different family. Jupiter and Saturn are what we call gas giants, vast balls made mostly of hydrogen and helium, the lightest stuff there is. But Uranus and Neptune are a little smaller and made of heavier material, and we give them their own name. We call them ice giants. And that word ice is a bit misleading, so let me decode it gently right now because we'll come back to it later. When a planetary scientist says ice here, they don't quite mean the cold, hard, slippery stuff in your freezer. They mean water and ammonia and methane, substances that are frozen or slushy in the cold of deep space, all wrapped around a core of rock. So an ice giant is, very roughly, a great deep ocean ball of these icy materials over a rocky heart, with an atmosphere on top. Hold that loosely. We'll sink down into its strange interior much later tonight, and there's a genuinely beautiful surprise waiting down there. And the color. Uranus is famous for its color, a pale, soft blue-green, a kind of washed-out cyan like the sea in a shallow tropical bay seen on a hazy day. And that color comes from a single ingredient in its upper atmosphere: methane. There's methane gas up in the haze of Uranus, and methane has a particular habit. It soaks up red light. It absorbs the red and the warmer colors out of the sunlight that hits it, and lets the blues and greens scatter back out toward us. So when you look at Uranus, that gentle cyan you're seeing is, in a sense, the leftover light. The colors the methane didn't swallow. It's the same reason a thing looks the color it looks. You're seeing what it didn't keep. Uranus keeps the red and hands us back the blue. Now here's the first piece of the settled story that makes people sit up. And it's true, by the way, this part is real, confirmed, not an artifact of anything. Uranus is tilted over on its side, wildly on its side. Almost every planet spins more or less upright, like a top spinning on a table, its axis pointing more or less up and down. The Earth leans a little. That gentle tilt is what gives us our seasons, but only a little, only by about 23 degrees. Uranus, though, doesn't lean. It lies down. Its axis is tipped over by nearly 98 degrees, which means it's essentially rolling around the sun on its side like a ball rolling along the floor rather than a top spinning on a table. We'll come back to this because it has some genuinely dreamlike consequences for what a year feels like on Uranus, and because the question of how it ended up that way is one of the great unsolved puzzles. But for now, just hold the image, a planet on its side, lying down in space, slowly rolling through its long, long orbit. And it is a long orbit. Uranus is so far from the Sun that it takes 84 Earth years to go around just once. 84 years. A single year on Uranus is longer than most human lifetimes. A person born when Uranus was at one point in its orbit might live their entire life and die before the planet had made it all the way back around. There's something quietly humbling in that. That out there, one slow circle of one cold world is the length of a whole human life down here. Then there are the rings. Yes, Uranus has rings, though they're nothing like Saturn's bright, broad, dazzling halo. Uranus's rings are dark and narrow and faint, thin little hoops of black material, and there are a system of them circling the planet. And here's a small, lovely detail in the settled story. We knew about those rings before any spacecraft ever went there, and we found them in a clever and rather beautiful way. I'll save exactly how for later tonight, because it's the kind of detail that's nicer when you have time to enjoy it. But keep it in the back of your mind, a small, parked question. How do you discover rings around a planet you've never visited with the technology of decades ago? And then there are the moons. Uranus has a whole family of them, quite a large family in fact, with new little ones still being discovered even now. And they all carry a particular and rather poetic theme to their names, which I'll let you wonder about for a while before I tell you. 5 of them are the major ones, the big ones, and one of them in particular hides a feature so dramatic it's hard to believe. A cliff that may be among the tallest in the entire solar system. But all of that is for later. For now, just know the family is there, circling that sideways world in the cold and the dark. That's the tidy picture. The pale blue-green ice giant tilted on its side, ringed in dark and faint hoops, surrounded by its moons, swinging slowly through an 84-year orbit far out at the edge of things. That's roughly what you'd have read in any book, and for a long time, that's where the confidence ran out and the puzzles began, because alongside that tidy picture sat a few genuinely strange things that Voyager measured during those 6 hours, things that didn't quite make sense, that scientists wrote down as weird facts about Uranus and shrugged at for decades. There was its magnetic field, which we'll get to properly, and which is so lopsided and off-kilter that it makes Earth's tidy, sensible field look almost boring by comparison. There was the strange, empty space around the planet, the puzzle of those radiation belts with seemingly nothing to feed them, which is exactly the puzzle the 2024 study may have just quietly solved. There was the question of its missing heat, a mystery so stubborn it's still unsolved tonight as you and I lie here. And there was the deep cold of it. Uranus holds a record that when you first hear it, sounds like a mistake. But all of that is the body of our night, the slow middle, and I don't want to rush into it. We have hours, there's no hurry at all. For now, I just want you to hold the strangeness of the frame itself, the thing that makes Uranus different from every other planet we talk about. It isn't only that it's tilted or cold or far away. It's that our entire relationship with this world rests on such a thin and fragile foundation. 6 hours, one pass, one spacecraft decades ago, moving too fast to stop, gathering everything it could in a rush and then falling away into the dark, never to return. And now the growing suspicion that even those precious 6 hours caught the planet in a rare and unusual mood, squeezed and distorted by a gust of solar wind, so that the very picture we built, the picture in all the books, may be a picture of Uranus mid-flinch, rather than Uranus as it truly, ordinarily is, which raises the question that's going to pull us gently through the whole rest of tonight, the open door, at the end of this first quiet room. If the one good look we ever got caught the planet in an abnormal state, then what does normal Uranus actually look like? What's the real, everyday face of that world, the one we've never properly seen? We genuinely don't know. And the only way we'll ever find out is to go back, which, as I'll tell you near the end, is exactly what some of the best minds at NASA most want to do. And it's a longer, harder road than you might imagine. So that's where we are, you and I, on this quiet night. Lying here in the warm dark, looking out toward a pale, sideways frozen world we've met exactly once for one strange afternoon, nearly 40 years ago, and only now beginning to suspect that we may have misread almost everything. We'll go slowly from here. We'll take each strange thing about Uranus in turn, gently, one room at a time, and for each one we'll ask the same quiet question. Is this real and confirmed, true no matter what? Or could this be an artifact of that one strange day? Some of it will hold, some of it will wobble, and by the end of the night, you'll have a clearer sense of this planet than almost anyone. And the lovely thing is, you can fall asleep at any point along the way because none of it is going anywhere. So settle in a little deeper, let that lamp stay on if it's still on, and let's begin properly with the strangest single thing Voyager measured in those 6 hours, the magnetic field of Uranus, and the empty space around it that puzzled scientists for almost 40 years, because that's the puzzle the 2024 study may have just gently, quietly taken apart. Let me tell you what they used to think, and then let me tell you why it may all have been the planet flinching. For decades, the textbook entry read something like this. Uranus has a magnetosphere, a great invisible bubble of magnetism, the kind of thing every planet with a churning interior tends to wrap around itself. Earth has one, Jupiter has a vast one, Saturn, Neptune, all of them, each cradled in its own magnetic cocoon that catches the wind streaming off the sun and holds it at bay. And when Voyager 2 swung past Uranus in those few short hours, its instruments found that bubble too. So far, so ordinary. But what they found inside it was anything but ordinary. The bubble was, in a word, empty. Strangely, eerily empty. There were these belts of high-energy electrons looping around the planet, radiation belts, the same family of thing that surrounds the Earth, where charged particles get trapped in the magnetic field and race around it at tremendous speed. Voyager measured them, and they were intense, fierce even, among the most intense radiation belts anyone had seen. And yet there was almost no plasma. Now plasma is just a fancy word for gas that's been energized so much its atoms have come apart into charged pieces. A soup of electrons and ions, the most common state of ordinary matter in the universe, even if it's rare here in your cozy room. Stars are plasma, the solar wind is plasma, and usually when you find radiation belts buzzing around a planet, you find plasma feeding them, a reservoir of charged particles topping them up. At Uranus, that reservoir seemed to be missing. The belts were there, humming away, but the plasma that ought to fill the rest of the magnetosphere and supply those belts simply wasn't. It was like walking into a house where the lights are blazing in every window, but you can't find the wires, can't find the power line, can't find anything that should be keeping them lit. That was puzzle number 1. And it led straight to puzzle number 2, which only deepened the mystery. Because where does a planet's plasma usually come from? Often from its moons. Active moons, ones with geysers or thin atmospheres or surfaces being slowly chipped away, can spray material into space, and that material becomes the plasma that fills the magnetic bubble. Saturn's moon does exactly this, feeding a great donut of particles around its parent. So scientists looked at Uranus's big moons, at Titania, at Oberon, the 2 largest, named, like all the others, for characters out of Shakespeare and the poet Alexander Pope. And they looked for some sign that these moons were doing the same thing, breathing material out into the system. And they found nothing, no detectable signature of the moons acting as plasma sources. The moons appeared from that one brief glimpse to be quiet, dead, inert lumps of ice and rock orbiting in silence. And so the picture set, like cement, into the textbooks. Uranus, the strange planet with fierce radiation belts and no plasma to feed them, ringed by lifeless, geologically silent moons. A weird, empty, anomalous corner of the solar system. For nearly 40 years, that was simply the truth of the matter. It got copied from paper to paper, from book to book, from one documentary to the next. The empty planet. The dead moons. Here's the thing about a single measurement, though. A single measurement is a single moment. It's one photograph. And a photograph, however sharp, however carefully taken, only ever shows you the instant the shutter opened. It cannot tell you whether that instant was typical. It cannot tell you whether you caught the room on an ordinary Tuesday or in the one strange minute of the year when everything happened to be out of place. For 38 years, nobody thought to ask that question of Uranus. Why would they? It was the only data we had. There was nothing to compare it against. No second visit, no before, and no after. When you have exactly one photograph of something, that photograph becomes your entire reality. It doesn't occur to you that it might be the unusual one because you have nothing to call usual. And then, in 2024, Jamie Jasinski and his colleagues at NASA's Jet Propulsion Laboratory went back. Not to Uranus. Nobody's been back to Uranus. They went back to the data, to those same old streams of numbers Voyager 2 had radioed home across the dark in 1986. The magnetometer readings, which measure magnetic fields. The plasma readings, which count the charged particles. The raw, decades-old record of those 6 hours. And they did something quietly brilliant. They didn't just read what the numbers said about Uranus. They read what the numbers said about the conditions Voyager flew through to reach it. Because the solar wind, in that stream of plasma blowing constantly off the sun, isn't steady. It gusts, it surges. Sometimes the sun throws out a great burst of it, a squall, and that squall races outward across the solar system and slams into whatever's in its path. What Jasinski's team concluded in a paper published in the journal Nature Astronomy was that Voyager 2 had arrived at Uranus just days after exactly such a squall. An intense burst of solar wind had come barreling out from the sun and reached Uranus right before the spacecraft did, and when that gust of high-pressure wind hit the planet's magnetic bubble, it squashed it, compressed it hard, like a fist closing around a balloon. And here's the number that should stay with you tonight, the number to carry down into sleep. The team calculated that the magnetosphere was compressed to a degree that happens only about 4% of the time. 4%. 96 nights out of 100, Uranus sits there in something closer to its ordinary, relaxed state. And on the one afternoon we showed up, the one and only time in human history, we caught it in the 4%. We caught it squeezed. We caught it mid-flinch. Think about what a squeeze like that would do. When you compress a magnetosphere suddenly and hard, you don't just shrink it, you change what's inside it. The pressure can drive the plasma out, flush it from the system, empty the bubble of the very soup that's normally there. And in that emptied, compressed state, the radiation belts can flare up brighter than usual, the trapped electrons energized by the violence of the squeeze, which means, and I want you to hear this gently because it's the whole quiet heart of the night, the two great puzzles, the empty magnetosphere and the fierce belts, may not be deep mysteries of Uranus at all. They may simply be a snapshot of a planet caught in a rare and temporary state. Not the way Uranus usually is. The way Uranus happened to be for a few days, 4 decades ago, when we glanced at it once and looked away. And the dead moons. Oh, the moons. If the plasma was flushed out by the squeeze, then of course Voyager found no sign of the moons feeding it. There was nothing there to find, not because the moons weren't supplying it, but because the supply had been temporarily swept away. Under normal conditions, Titania and Oberon and the others might be active contributors after all. Quietly breathing material into the dark, exactly as moons elsewhere do, while we sat here for 38 years, calling them lifeless on the strength of one badly timed measurement. We may have buried those moons alive, in our textbooks at least, filed them under dead, when they may have simply been holding their breath the one moment we looked. Now, I want to be careful and honest with you here, because that's the kind of companion I'd like to be on a night like this. This is a recent study, a strong one, peer-reviewed, and published in a serious journal. But it's a reinterpretation, not yet the new settled gospel. It's the leading new model, the most compelling explanation we have. It hasn't overturned the textbook so much as gently knocked on the door and said, "Are you quite sure about all this?" So hold that thought, that beautiful, quietly unsettling thought, and let's move deeper. Because there's another piece of the magnetosphere story that is not a reinterpretation. It's not waiting for a follow-up mission to confirm or deny. It is as solid as anything we have, a genuine, confirmed architectural strangeness of Uranus that no flyby timing, no solar wind compression, no cosmic coincidence of scheduling can explain away. This is what Voyager 2 found when it read the magnetic field of Uranus, and it is, honestly, one of the most peculiar things in the solar system. Think about how a magnetic field is supposed to work on a planet. Picture Earth. Our magnetic field, the one that makes compasses point north, the one that forms the invisible shield deflecting charged particles from the sun, it runs roughly through the planet's poles. If you drew a line through the center of our magnetic field, it would point almost along the same axis as the line through the geographic north and south pole. It's not perfectly aligned, no. A compass doesn't point exactly at the true North Pole, and every few 100,000 years the whole field flips. But in broad terms, Earth's magnetic axis and Earth's rotation axis are close companions, off by only about 11 degrees. Neighbors, really. Jupiter does something similar. Saturn does too. These are the planets we think of as the well-behaved ones, magnetically speaking, with dipole fields that mostly get on with the job of being orderly and pointing in sensible directions. Uranus does not do this. Uranus's magnetic field is tilted roughly 59 degrees away from its rotation axis. Let that sit for a moment. 59 degrees, that's not a small lean, that's enormous. Imagine if Earth's magnetic field were oriented so that the North Magnetic Pole sat somewhere over the Indian Ocean, swinging wildly across the globe as the planet turned. Compasses would be nearly useless, navigation would be chaos. But the tilt, staggering as it is only the first part. The second part is even stranger. On Earth, on Jupiter, on Saturn, the magnetic field appears to originate from somewhere near the center of the planet, which makes physical sense because the magnetic field is generated by the churning, electrically conducting interior, and the center is where the pressure and heat are highest, where things are most in motion. The field is centered more or less where you'd expect. Uranus's magnetic field is not centered. It doesn't come from anywhere near the middle of the planet. It's offset, shifted by roughly 1/3 of the planet's radius toward one pole. 1/3. If Uranus were the size of a basketball, the center of its magnetic field would be sitting more than 2.5 inches away from the center of the ball. Not at the heart of the planet at all. Somewhere off to the side, deep in one hemisphere, as if something in the interior decided to put the engine in the wrong room. And what happens when you combine a field tilted 59 degrees from the rotation axis with a field offset by 1/3 of the planet's radius? You get something chaotic, something that tumbles. Because Uranus rotates, it completes a full rotation every 17.25 hours or so, give or take a few minutes, its day ticking along at its own pace beneath that wild sideways orbit. And as it rotates, the magnetic field rotates with it. But because the field's axis doesn't line up with the rotation axis, the whole magnetic structure sweeps through space like a wobbling top, like a gyroscope that's lost its composure. The field strength doesn't stay constant. It swings dramatically over the course of each rotation, sometimes stronger, sometimes weaker, the geometry shifting in complicated and chaotic patterns. On Earth, the solar wind, in that constant stream of charged particles flowing out from the Sun, hits our magnetosphere, and the interaction is relatively orderly. The solar wind bends around us, gets funneled toward the poles, produces the aurora. It's dynamic, yes, but it has a rhythm, a structure. The magnetopause, the outer boundary where Earth's magnetic pressure balances the solar winds, sits in a predictable place and maintains a broadly consistent shape. Uranus's magnetosphere doesn't do that. It can't. Because the field is both tilted and off-center, the region where the magnetic field connects to the solar wind, where the field lines thread through the boundary and link the interior to the interplanetary environment, shifts constantly and dramatically as the planet rotates. Every 17 hours or so, Uranus essentially presents a completely different magnetic face to the Sun. The connection geometry cycles through configurations that would each take hours or days to cycle through on a planet with a normal field. Scientists have a word for what this produces. They call it a chaotic magnetosphere. Not chaotic in a casual, vague way, chaotic in a technical, genuine, the field is doing things we have a hard time predicting way. The solar wind doesn't get a steady, sensible boundary to push against. It gets a moving, tumbling, asymmetric structure that changes faster than almost any other planet in the solar system. And we measured all of this in roughly 6 hours, which is remarkable when you think about it. In less time than a typical workday, Voyager 2's magnetometer instruments were reading off data that planetary scientists are still untangling 40 years later. The field strength values, the orientation measurements, the plasma readings, all captured in that narrow corridor of time and transmitted back across nearly 2 billion miles of space to antennas on the surface of Earth. So here is where we stand on the magnetosphere picture. There are 2 layers to it now. The first layer, some of what we thought we knew, the empty plasma environment, the intense electron radiation belt sitting there with nothing obvious to feed them, the moons apparently doing nothing. That first layer may be a snapshot of an unusual day, a compressed day. A day when the solar wind had come through hard and swept the system clean before Voyager arrived. The 2024 study led by Jamie Jasinski and his colleagues at NASA's Jet Propulsion Laboratory suggests this is the most plausible explanation, and it means the puzzle of the empty belts may not be a puzzle at all. Just bad timing on our part, a planet mid-flinch. But the second layer, the 59-degree tilt, the offset by 1/3 of the radius, the chaotically tumbling magnetosphere, the field strength swinging wildly with every rotation. That is not an artifact of timing. That is not something the solar wind squeezed or temporarily rearranged. That is the architecture of Uranus itself. That is baked in. Whatever is happening inside this planet to produce a field that lopsided and misaligned, it's a genuine mystery of planetary physics, confirmed and solid, waiting for someone to explain it. The leading ideas involve the structure of the interior. The fact that Uranus is an ice giant, that its conducting layer may be a shell of warm, pressurized, water-rich fluid sitting at intermediate depth rather than a metallic core under enormous pressure like Jupiter's, and that a convecting shell-like structure might naturally produce a more complex multipolar offset field. But this is hypothesis and model, not settled science. The truth is, we don't fully understand why Uranus's magnetic field looks the way it does. And Neptune, as it turns out, has a similarly strange magnetic field, tilted and offset, which suggests there may be something about ice giants in general, something about the kind of interior these worlds build that produces fields the gas giants don't. 2 planets in the outer solar system with scrambled, tumbling magnetospheres, and we've visited each of them exactly once, each for a handful of hours, and we are trying to understand them from that. It is, honestly, a little humbling, a bit like trying to understand a person's entire life from one photograph taken on one afternoon, not knowing whether that afternoon was ordinary or the strangest day they ever had. Now, there is another confirmed strangeness about Uranus, something the magnetosphere reinterpretation does nothing to change, something that no solar wind event could cause or reverse or temporarily impose. Something that was there long before Voyager 2 launched, long before anyone thought to ask why Uranus's radiation belts were empty, long before the word magnetosphere had even been coined. It is the tilt. That extraordinary, almost incomprehensible tilt. Uranus's rotation axis, the imaginary line through its poles around which the whole planet spins, is tilted approximately 97 8/10 degrees away from vertical, from the perpendicular to its orbit, nearly horizontal, nearly all the way over. Every other planet in the solar system is upright or close to it. Earth leans about 23 degrees, which gives us our seasons. Mars leans a little more than that. Saturn tilts about 26 degrees. Jupiter barely leans at all. But Uranus is lying down, rotating on its side. Its poles are where every other planet's equator would be, and its equator sweeps through a region of space that would be occupied by the poles of a normal planet. To get a feel for this, imagine spinning a top on a table. Normally the top stays upright, spinning along the vertical axis, wobbling slightly but roughly perpendicular to the table's surface. Now imagine tipping that top over until it's almost lying flat on the table, but it's still spinning. The spin axis now nearly parallel to the table. That's Uranus, rotating sideways through space, the poles pointing roughly toward and away from the Sun rather than up and down. And because Uranus takes 84 Earth years to complete one orbit around the Sun, the consequences of this sideways tilt are extraordinary and strange. Each pole spends roughly 42 years facing the Sun, bathed in continuous sunlight without a single day or night in the conventional sense. Then, as Uranus continues around its orbit and the geometry shifts, that same pole slowly turns away from the Sun. And for the next 42 years, it sits in darkness, continuous darkness, a polar night that lasts longer than a human lifetime, or at least as long as a full working life, from the first day of a career to retirement and beyond. The equatorial regions of Uranus do experience something more like the rapid day-night cycle we're familiar with, the 17-hour rotation producing short, swift alternations of light and dark. But the poles live in a time scale that is alien to anything we experience. 42 years of unbroken sun, followed by 42 years of unbroken dark. Voyager 2 arrived just before a southern hemisphere solstice. The South Pole was pointed more or less at the Sun, the North Pole deep in its long night, which meant that as Voyager swept past and the cameras looked back, most of what they could see was a sunlit southern hemisphere, and the planet, because of that near-solstice geometry, appeared oddly featureless, almost uniform. A pale blue-green sphere with very little visible banding or storm structure, especially compared to the dramatic swirling of Jupiter, or the elegant rings and bands of Saturn. Some of the boring planet reputation that Uranus acquired after the Voyager flyby may owe something to that timing too. Later images from the Hubble Space Telescope and the Keck Observatory revealed storms, bright cloud features, and seasonal change, a more dynamic world than the 1986 photographs suggested. The near-solstice geometry hid some of the planet's complexity, just as the solar wind compression may have hidden some of its magnetospheric complexity. Two different ways the timing of one single encounter shaped what we thought we knew. But even setting that aside, even granting that Uranus is more active than that first bland image implied, the question of the tilt itself remains. Why is it lying down? What happened? The leading answer is violence. Something hit it. Early in the solar system's history, when the planets were still forming, the debris left over from the Sun's birth was still thick. a vast population of rocky and icy bodies in all sizes, from grains of dust to objects nearly as large as Earth, all moving through the primordial disk in complex, crossing orbits. Collisions were common, catastrophic, and in many cases world-altering. The leading scientific models for Uranus's tilt invoke one or more of these giant impacts: a collision with an object whose mass might have been anywhere from roughly equal to Earth's to perhaps twice Earth's, a body large enough that when it hit, the torque of the impact tilted the entire planet's spin axis by nearly 90 degrees. Some models favor a single catastrophic strike, one enormous impactor arriving at the right angle at the right velocity to knock the planet over and leave it there. Others suggest a sequence of smaller collisions, each nudging the axis a little further. Still others point to the possibility that an early, large moon could have been gravitationally lost from the system in a way that torqued the planet sideways over time. None of these models has been definitively confirmed. The cause of the tilt is still an open scientific debate, agreed on in broad outline. Giant impact is probably involved, genuinely uncertain in the details. How large was the impactor? Were there one or more? Did a moon play a role? The honest answer is that we don't know, not yet. What we know is the result: 97 8/10 degrees. A planet turned on its side, marching around the Sun at an angle no other world in our neighborhood matches, its poles tracing long ellipses through sunlight and darkness on a timescale measured not in months, but in decades. And there is something quietly extraordinary about contemplating that. If you were standing, hypothetically, impossibly, because Uranus has no real surface to stand on, but let's say you were floating at the right altitude in its atmosphere near one of the poles, you would see the sun rise once, and you might not see it set for 42 years. Not a dramatic, blazing sun like we see from Earth. It would be much fainter at Uranus's distance, dimmer and smaller in the sky, but present, there, constant, circling low on the horizon for decades. And then, gradually, as the orbit progressed, it would sink, and the night would come, and the stars would be there, and the distant, cold, beautiful dark for another 42 years. It's one of those facts that doesn't quite resolve into ordinary comprehension. It just sits there, slightly too large for the mind to fully hold, like a lot of the truths about the outer solar system. Now, there's a third strange thing about Uranus, the third great confirmed puzzle. And it has nothing to do with the magnetosphere or the tilt. It has to do with something much simpler and much harder to explain: heat, or rather, the absence of it. Every planet in the outer solar system formed roughly 4.5 billion years ago from the same collapse of gas and dust. And the process of formation, the accretion, the compression, the release of gravitational energy as material fell inward, generated heat. An enormous amount of heat. That primordial heat is still stored in the interiors of Jupiter, Saturn, and Neptune today. These planets are still slowly radiating it away into space, releasing the energy of their own creation across billions of years. Jupiter radiates nearly twice as much heat as it receives from the Sun. Saturn radiates almost twice as much. Neptune, Uranus's near twin in size and mass and composition, radiates approximately 2.5 times the energy it receives from the Sun. These planets are still glowing, faintly, from the warmth of their own birth. Uranus does not. Uranus's measured heat output is, depending on how you measure it and what period of its orbit you observe it in, very close to, only very slightly above, the energy it receives from the Sun. It's not pumping out internal heat the way its siblings are. Whatever warmth it accumulated during formation, it is not leaking it into space in any significant way, and nobody knows why. That's not a figure of speech. That is genuinely, honestly, the state of the science. The internal heat anomaly of Uranus is one of the open questions of planetary physics, argued over in journals and conference rooms modeled with supercomputers and as yet unsettled. The colder temperatures that result from this are measurable and real. Uranus has the coldest atmosphere of any planet in the solar system. Its minimum measured temperature deep in a specific layer of its atmosphere is around -224 degrees Celsius. That's roughly 49 Kelvin, 49 degrees above absolute zero. The absolute coldest temperature achievable, the point at which molecular motion theoretically stops altogether, Uranus is sitting about 49 degrees above that floor. What makes this remarkable in a specifically puzzling way, is that Neptune, farther from the Sun, receiving even less sunlight than Uranus, is not as cold. Neptune's temperatures are actually warmer in parts of its atmosphere than Uranus's coldest measured region. And the only explanation that makes sense for this is the one we just mentioned. Neptune is radiating internal heat, warming itself from within. Uranus is not. So the planet that is closer to the Sun, that receives more solar energy, that by all rights should be at least as warm as its sibling, is actually colder. The hypothesis that has attracted the most attention, though I want to be careful to note it remains a hypothesis, involves the structure of Uranus's interior, and it ties back to the giant impact we talked about a few moments ago. The idea is this. When a large impactor struck Uranus in the early solar system, it may have done more than just tip the planet sideways. It may have rearranged the interior, mixed things up in a particular way, or altered the layering of the planet's deep structure so that a layer of relatively lighter material now sits at an intermediate depth and acts as a kind of thermal blanket. Not a blanket that keeps the planet warm by adding heat, but a barrier that traps the heat and prevents it from reaching the surface and escaping. The heat is still there, this model suggests. It's just locked in. The planet is running a fever it cannot express, insulated from the inside. This is elegant, and it might be right, but it's still modeling an inference in we cannot see inside Uranus. We have no seismograph on its surface, no probe that descended into its clouds and measured the interior directly. We're reading its thermal signature from the outside and trying to work backward to what the inside must be doing, and right now the inside isn't fully cooperating with our models. What we can say with confidence is this: Uranus is the coldest planet in the solar system. Its coldest measured atmosphere sits at around -224 degrees Celsius, colder than Neptune despite being closer to the Sun. And the reason is almost certainly that Uranus is not releasing its primordial heat the way every other outer planet is. The exact mechanism by which this happens, why Uranus retained it, how the interior is structured to prevent it from escaping, that remains an open and genuinely interesting scientific question, the kind that only a mission with a probe that descends into the atmosphere could begin to properly answer. And that, in a way, is the quiet thread that runs through all of these mysteries. The tilt we can see from Earth, the magnetic field geometry we can measure, at least partially, from a passing spacecraft, the temperatures we can read from telescopes and infrared instruments. But the interior, the deep interior, where the physics that drives all of these surface phenomena is actually happening, the interior we have never sampled directly. We have never sent anything into the clouds of Uranus, not a probe, not a descent instrument, nothing. Everything we know about what's inside this planet is inferred, modeled, extrapolated. We are reading the exterior symptoms and guessing at the disease. And the symptoms are strange enough that the guesses span a wide range. Let's stay with that for a moment, because the interior of Uranus is genuinely, fascinatingly strange in its own right, quite apart from anything we're uncertain about. The classification ice giant already tells you something unusual is going on. Uranus is not a gas giant the way Jupiter and Saturn are, dominated by hydrogen and helium throughout most of their immense volumes. Uranus has a different composition at depth. Mixed into its interior with the high-pressure, high-temperature regions below the visible atmosphere are substances that we loosely call ices in planetary science, though the word is somewhat misleading. Water, ammonia, methane. Not frozen in the way ice cubes are frozen, not cold and crystalline, but compressed under pressures so extreme and heated to temperatures so high that they exist in something more like a dense, hot, pressurized fluid. Ionic, electrically conducting, strange. It's this layer, a deep mantle of these pressurized, electrically active water and ammonia and methane fluids, that planetary scientists suspect is where Uranus's peculiar magnetic field is generated. It's not from a metallic hydrogen core at the very center, as in Jupiter, but from this shell of conducting fluid at intermediate depth, which would help explain why the field is so offset and so tilted. A shell-like dynamo, a conducting layer that doesn't sit at the center, would naturally produce a more complex, more asymmetric field than a core-centered one. And then there's what might be happening to the methane at even greater depths. In 2017, a team of researchers conducted an experiment at the SLAC National Accelerator Laboratory in California, using the powerful Linac coherent light source, an extraordinarily intense X-ray laser, to recreate, briefly and in a very small region of space, the conditions that exist deep inside ice giants like Uranus and Neptune. Pressures millions of times greater than the atmosphere at Earth's surface, temperatures of thousands of degrees. Under those conditions, methane, which is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, does something unexpected. It breaks apart, and the carbon, freed from its hydrogen, can crystallize. Under extreme pressure, carbon crystallizes into its densest, most ordered form, diamond. The experiment by Dominic Krauss and colleagues and published in Nature Astronomy in 2017 provided laboratory evidence that under conditions comparable to those inside Uranus and Neptune, methane breaks down and carbon forms tiny diamond crystals. The hypothesis supported by this and related work is that deep inside Uranus, diamonds may be forming continuously and slowly sinking through the interior under gravity. Not in the way you'd imagine diamonds, not faceted, not sparkling in some metaphorical underground vault, but tiny crystals of carbon forming in the hot, pressurized depths and drifting downward through the surrounding fluid. Diamond rain, the popular shorthand calls it. And it's a wonderful image, and the physics behind it is genuinely supported by the laboratory experiments. The experiment showed the thing can happen. Whether it is actually happening in the interior of Uranus, at what rate, and with what consequences for the planet's thermal or magnetic behavior, that remains inferential. The lab recreated the conditions. The lab showed the reaction. But we haven't seen inside Uranus to confirm it directly. Still, the possibility that somewhere beneath that pale cyan face, in depths of crushing pressure and fierce heat, it may be raining diamonds. Slowly, silently, the carbon of ancient methane crystallizing and falling through the dark interior of a world 19 times farther from the sun than we are. That's the kind of thing that makes the quiet hours feel a little wider, a little more full of the universe. And now we arrive at something that for a long time simply didn't add up. When Voyager 2 swept through the Uranian system in January 1986, the magnetometer and plasma instruments were working. They were measuring, and what they found in the space around Uranus was, to put it plainly, strange, but not in any of the ways scientists had expected. The radiation belts were there. Intense, concentrated rings of energetic electrons trapped by the magnetic field, similar in structure to the Van Allen belts around Earth. Those were real. Those were measured but surrounding them, threading through the broader magnetosphere the way plasma threads through the magnetic environments of Jupiter and Saturn, was almost nothing. A near emptiness. Scientists looked at the data and scratched their heads because radiation belts need a source. They need particles, and particles usually come from somewhere. From a moon's volcanic activity, from the solar wind, from some kind of supply. But Uranus appeared to have intense belts and almost no plasma to feed them. The large outer moons, Titania and Oberon, showed no detectable signs of being active sources. They seemed dead, quiet, geologically inert as far as the plasma environment was concerned. So the puzzle got folded into the category of Uranian weirdness and left there. Here is yet another strange thing about this strange planet, the textbooks implied. Intense radiation, no plasma, dead moons, noted, and that picture sat essentially undisturbed for nearly 4 decades. Then came Jamie Jasinski and his colleagues at NASA's Jet Propulsion Laboratory and their 2024 paper in Nature Astronomy. And the reanalysis they published suggested something quietly remarkable, that the Voyager 2 flyby had arrived just days after an unusually intense burst of solar wind had compressed the Uranian magnetosphere, compressed it to a degree that, based on the data and modeling, the team concluded occurs only about 4% of the time. 4%. That means if you chose a random moment to visit Uranus and measure its magnetosphere, you would encounter this particular kind of solar wind squeeze only about 1 time in 25. Voyager 2, arriving on its single, unrepeatable pass, apparently arrived during one of those rare moments. And what does that compression do? It doesn't just reshape the outer boundary of the magnetosphere the way squeezing a balloon changes its profile. It drives plasma out. The pressure pushes the plasma away from the planet, evacuates it from the magnetospheric system, and leaves behind something that looks unexpectedly empty. Intense electron radiation belts sitting in a zone with almost no surrounding plasma to speak of, which is almost exactly what Voyager 2 saw. The implication is gentle but significant. Titania and Oberon, those large, quiet moons that Voyager found seemingly dead, seemingly contributing nothing to the plasma environment, may not be dead at all. Under normal conditions, they might be active contributors, feeding particles into a magnetosphere that looks considerably more populated than what Voyager recorded. We wrote them off based on a measurement taken during what may have been a transient evacuation. The moons might simply have been sitting in a swept clean room on the one day anyone came to visit. We don't know yet. The 2024 paper presents this as the most plausible interpretation of the data, a strong, peer-reviewed argument published in one of the field's respected journals. But it isn't textbook overturned certainty. It's the leading new picture, and it changes the way scientists think about what Uranus normally looks like. The distinction matters. Some things Voyager measured are confirmed regardless of the solar wind's behavior that week. The compression hypothesis is the new framework for the plasma environment specifically. So hold that thought for a moment, because now we need to talk about the magnetic field itself. And this part is confirmed regardless. This part is not a function of timing or solar weather. This part is simply what Uranus is. The magnetic field of Uranus is, by any reasonable standard, deeply odd. Most planetary magnetic fields are generated in the deep interior, and they tend to be roughly aligned with the planet's rotation axis. Not perfectly, Earth's magnetic north sits about 11 degrees away from the geographic North Pole, which is already enough to make compass navigation a matter of correction rather than raw pointing. Jupiter and Saturn are similarly tilted by modest amounts. The general picture is of a magnetic field that behaves somewhat like a bar magnet, placed more or less along the planet's spin axis, with the field lines flowing in a reasonably predictable pattern. Uranus does none of this. Uranus's magnetic field is tilted approximately 59 degrees from its rotation axis, not 11 degrees 59. That means the magnetic axis is so dramatically misaligned from the spin axis that if you traced the magnetic pole's position in the sky as the planet rotated, it would sweep out an enormous arc every rotation, not hovering near the geographic pole as Earth's does, but lurching far across the sky, a wide, lopsided circle. And it isn't just the tilt. The field is also offset. It doesn't originate from near the center of the planet the way Earth's field does. The source, the region of the interior generating the magnetic field, sits displaced roughly 1/3 of the planetary radius toward one pole, which means the field is not only pointed in an unusual direction, it is generated off-center like a flashlight held to the side of a room rather than from the middle of the ceiling. Put those two things together and what you get is a magnetosphere that doesn't hold a stable geometry. As Uranus rotates, and it rotates every 17.24 hours, a day shorter than Earth's, though that number itself comes from the 1986 Voyager measurement, so even this is subject to the caveats of our single visit. As the planet turns, the tilted off-center field sweeps through space in a tumbling, lurching motion. The connection point between the magnetic field and the incoming solar wind changes dramatically over the course of each rotation. The whole magnetosphere writhes and shifts, connecting and disconnecting from the solar wind in a chaotic, rapidly changing pattern. Earth's magnetosphere is, comparatively, a model of orderly behavior. Jupiter's is vast but roughly predictable in its structure. Saturn's is exceptionally well aligned with the rotation axis, almost unnervingly so. And then there is Uranus, with its tumbling, asymmetric, off-center magnetic cocoon that behaves unlike any of them. Scientists believe this unusual geometry may arise from the nature of Uranus's interior, that the magnetic field is generated not deep near the rocky core as Earth's is, but in a shell of electrically conducting fluid somewhere in the middle layers of the ice giant, a thin shell dynamo rather than a deep core one. The physics of that kind of generator, theory suggests, could naturally produce a field that is dramatically tilted and offset, but confirming that picture requires data we don't yet have from inside the planet itself. What we do know, concretely, measurably, confirmed by Voyager's instruments, is that the field strength varies wildly as the planet turns. At some orientations during a rotation, the field connecting to the solar wind is intense, at others, weaker. The geometry shifts continuously. The magnetosphere doesn't just rotate like a top, it tumbles, and somewhere inside all of that tumbling, the charged particles interact with the magnetic structure in ways that may create auroras unlike anything we see on other worlds. Auroras that might appear at multiple different latitudes, disconnected from the poles, dancing across the planet's face as the field geometry writhes through its daily cycle. And all of that, every strange detail of the tumbling magnetosphere, the asymmetric field, the plasma mystery that may or may not be real, all of it came from one flyby in one afternoon in January 1986, during what may have been an unusual and transient moment in the planet's life. It is humbling, genuinely humbling, when you sit with that for a moment. But here is where the story shifts. Because some things about Uranus have nothing to do with the magnetosphere. Some things cannot be explained away by solar wind timing or a 4% statistical fluke. Some things were already strange before Voyager 2 arrived, and they will be strange long after any future spacecraft reaches the planet and begins, slowly, to revise the textbook. These are the confirmed oddities, the ones that are simply, irreducibly, factually true about this world, regardless of what the solar wind was doing in late January 1986. Start here. Start with the tilt. Uranus is rotating on its side, not slightly tilted. Every planet in the solar system has some tilt, the way a spinning top wobbles a little when it's not quite perfect. Earth is tilted about 23.5 degrees, and that tilt is the reason we have seasons. The reason summer in the northern hemisphere is warmer than winter, the reason the days grow long in June and short in December. Mars is tilted at about 25 degrees close to Earth's, which is one of the reasons Mars also has seasons. Even Saturn, that magnificent ring giant, leans at about 27 degrees. These are gentle tilts, dignified tilts. Uranus has an axial tilt of 97.8 degrees. 97.8 degrees. The way you might think about that, the image that makes it feel real rather than just a number, is this. Most planets spin like a top, their poles pointing broadly upward and downward relative to the plane of the solar system, the flat disk of orbiting space that the planets all move through. Uranus spins more like a ball rolling along a table. Its poles are not above and below in the usual sense. They are more or less to the left and right. The equator of Uranus runs nearly from top to bottom instead of around the middle. If you were standing, impossibly of course, but imagine it, somewhere near Uranus's north pole, you would be facing, more or less, the direction the planet is traveling in its orbit. Not looking straight up at the stars, looking forward into the motion. The sun, from that vantage, would arc not east to west across the sky the way it does for us, but in a strange low spiral depending on what season it is. And this brings us to the polar nights. Because Uranus is tilted so extremely, and because it takes 84 Earth years to complete one orbit of the Sun, the arrangement of sunlight on the planet's surface is unlike anything in the solar system. Think about how seasons work on Earth. We tilt toward the Sun in summer, away in winter, and the cycle is 6 months long. But that tilt, 23.5 degrees, is gentle enough that every part of Earth receives at least some sunlight every day of the year, even in the depths of winter at high latitudes. The sun gets low in the sky, the days grow very short, but the sun still rises and sets. The cycle repeats every year. Now imagine tilting the whole arrangement nearly 90 degrees and then stretching a single orbit to 84 years. At Uranus's poles, the result is this. When one pole is aimed toward the sun, which happens once every 84 years, the pole enters roughly 42 continuous years of daylight, not long days and short nights, no nights. Sunlight continuously for 4 decades. The sun just circles at a fixed angle in the sky, neither rising nor setting, just there. And then, as the planet swings to the other side of its orbit over the following decades, that same pole slowly, gradually tilts away. The sun drops toward the horizon, and eventually, around the 42-year mark, the sun sets. And then it does not rise again for another 42 years. 42 years of darkness, unbroken, a winter so long it would contain the entirety of a human life in most of recorded history. Right now, as of 2024, Uranus is partway through its transition. The southern hemisphere, which received sunlight for roughly 4 decades, has been tilting away since the Voyager 2 encounter. The northern pole is coming into sunlight. This seasonal shift happens on a time scale that makes human seasons look like the blink of an eye. And here is what makes this stranger still. During those 42 years of polar darkness, the temperature does not simply plunge. The atmosphere of Uranus, for reasons that are themselves not entirely understood, is extraordinarily cold regardless. But the transition, the change in solar heating as one pole swings into light and the other swings into darkness, has been observed to trigger cloud activity, storms, and seasonal atmospheric changes that no one expected given how slowly the cycle turns. Hubble Space Telescope observations in later years detected bright cloud bands and storm features that were not visible to Voyager's cameras in 1986. The planet is not the blank, featureless sphere it first appeared. It breathes slowly in time with a 42-year rhythm that our entire civilization has not yet sat still long enough to watch through a single cycle. But the tilt itself, where did it come from? This is one of the genuinely open questions in planetary science. The tilt of 97.8 degrees is so extreme that it almost certainly did not arise gradually. Something dramatic happened to Uranus. And the leading hypothesis, though still debated, is that something hit it. A giant impact, something very large, of an object with perhaps the mass of the Earth, or possibly even twice the mass of the Earth, striking Uranus long ago when the solar system was young and chaotic, when large objects were still hurtling through space, colliding and building planets the first few 100 million years after the Sun formed. The impact in this model was so violent that it knocked Uranus's rotation axis onto its side, essentially tipped it over. And there it has remained ever since, rolling along its orbit with its poles roughly in the plane of the solar system, its seasons stretched to geological timescales. Some researchers have modeled this as a single catastrophic collision. Others have proposed multiple smaller impacts or the gravitational influence of a large moon that once existed and later was lost or disturbed the planet's orientation over millions of years through a different mechanism. The models are not fully settled. Different simulations produce different results depending on the assumed properties of the impactor and the young Uranus. What they all agree on is that whatever happened, it was not a gentle process. Something profoundly disrupted this planet early in its history, and the tipped axis is the mark it left, a fossil of a very ancient violence preserved in Uranus's spin ever since. There is something quietly affecting about that idea, if you let it settle. The planet you are drifting off toward tonight has been rolling on its side for billions of years. It was hit hard, so hard that its entire orientation changed, and then the solar system gradually calmed around it, and there it orbits, tilted with its 42-year polar nights and its tumbling magnetosphere and its cold, pale cyan atmosphere, carrying the memory of an impact so old that the solar system was a completely different place when it happened. Uranus does not offer that story up easily. You have to go looking for it. Now, here is where we arrive at something that has frustrated planetary scientists for decades, something that sits at the heart of the mystery of Uranus in a way that is different from the magnetosphere puzzle, because this one cannot be explained by flyby timing. This one is simply stubbornly there waiting for an answer. Uranus does not seem to be releasing any meaningful internal heat. To understand why that is strange, it helps to know that giant planets, Jupiter, Saturn, Neptune, are not just floating cold spheres, they are slowly cooling from the inside. When they formed, billions of years ago, the process of gravitational collapse concentrated enormous energy in their interiors. All that matter falling inward and compressing generated tremendous heat. And that heat, accumulated at formation, has been slowly leaking out ever since, cooling off over billions of years the way a rock that has been sitting in a fire slowly radiates its heat into the night air once you pull it away from the flames. Jupiter radiates about 1.7 times as much heat as it receives from the Sun. It is glowing faintly from the inside. Saturn is similar, emitting roughly 1.8 times what it absorbs. So much so that there is ongoing scientific discussion about why it is still as warm as it is, since it should have cooled more by now. The leading idea there involves helium rain in the interior, a process of helium droplets condensing and falling, releasing gravitational energy as they descend. That is its own fascinating story. And then there is Neptune. Neptune is almost a twin of Uranus in size, in mass, in composition. They are the two ice giants, a category unto themselves. Neptune's diameter is a bit smaller than Uranus's, its mass is slightly higher, but in terms of their general structure and nature, they are the closest analogues in the solar system to each other. Neptune radiates about 2.6 times the heat it absorbs from the Sun. Not a small difference, not a rounding error. It is glowing substantially from within, emitting more than 2.5 times the solar energy it takes in, suggesting it still holds a great deal of primordial heat from formation that it is steadily releasing into space. Uranus radiates almost nothing extra. Its measured heat output is barely above, almost indistinguishable from, the amount of sunlight it absorbs. It is, as far as measurements can determine, contributing essentially no additional warmth from its interior. How is that possible? How does Uranus, a planet nearly the same size and composition as Neptune, apparently retain almost none of the formation heat that Neptune still carries in abundance? They should be similar. They are not. There are hypotheses. There are several, in fact, and they are all interesting, and none of them are conclusively proven. One possibility involves the impact again. If Uranus was struck by something very large, the energy of that impact could have disrupted the interior in ways that changed how heat moves from the core toward the surface. Under some impact scenarios, the collision may have created a layer in the interior, some kind of thermal boundary or stratification that acts like insulation. Heat from the rocky core is simply unable to move upward through this barrier in any efficient way. It is trapped inside, unable to escape. Uranus could actually be harboring a great deal of internal heat that simply cannot get out. In this picture, Uranus is not cold inside. It is hot inside, but sealed. The impact that tipped it over may also have trapped its warmth. Another possibility is that the interior of Uranus is more layered than Neptune's, that different chemical compositions at different depths create stable boundaries that resist the convection that would normally carry heat upward. On Earth, convection in the mantle is what drives plate tectonics and helps move heat from the interior to the surface. If Uranus's interior is too stable, too layered to mix freely, the heat stays put. Neither explanation is entirely satisfying yet. Neither has been confirmed with the kind of data that would settle the question. And the reason that data does not exist is, again, because we have only been there once, briefly, in 1986, and the instruments on Voyager 2 were not designed to probe the interior. What the measurements did confirm, unambiguously, beyond doubt, is the result. The surface temperature at the top of Uranus's atmosphere, the cloud top temperature, is approximately negative 224 degrees Celsius. That is about negative 371 degrees Fahrenheit. It is roughly 49 degrees above absolute zero, 49 Kelvin, the coldest planetary atmosphere measured in the solar system. That number bears sitting with absolute zero, the point at which molecular motion essentially stops, the coldest anything can theoretically be, is at 0 Kelvin. Uranus's atmosphere sits just 49 degrees above that theoretical floor. In terms of temperature, it is deep in the realm of extreme cold, a place where most gases familiar from everyday life would long since have condensed and frozen. The methane that gives Uranus its color, absorbing red light and letting the cyan blues and greens reflect back, exists in a frigid haze at these temperatures. The ammonia and water ices that make up much of the interior deeper down are at pressures and temperatures that have no easy parallel in human experience. And here is the part that makes that temperature number stranger still. Neptune is farther from the Sun, significantly farther. Neptune orbits at about 30 astronomical units, 30 times Earth's distance from the Sun. Uranus is at about 19 astronomical units. Neptune receives less sunlight than Uranus proportionally because it is farther away, and yet Neptune's atmosphere is warmer. Neptune's cloud top temperature is still deeply cold by any human standard, but it is measurably warmer than Uranus's, and the reason is that internal heat. Neptune is warming itself from within, contributing its own energy to its atmospheric temperature, and the result is an atmosphere that is not as cold as Uranus's, even though it is farther from the Sun. Uranus, receiving more sunlight, warmer from that external source, is colder. Because it is contributing almost nothing from inside, the extra sunlight cannot compensate for the complete absence of internal warmth. It is a counterintuitive result to the closer planet being colder than the farther one, and it is a direct fingerprint of that missing internal heat, a concrete, measurable symptom of whatever process is sealing the warmth inside Uranus, or preventing it from having any, or doing something else entirely that we do not yet understand. There is something peaceful, in a strange way, about not knowing the answer. Or rather, there is something that feels right about sitting with an open question in the quiet of the night without needing to resolve it. The scientists who study this don't know yet. That is the honest answer. The most honest thing anyone can say about why Uranus leaks no heat is that we have some ideas, and none of them are fully confirmed, and the only way to move toward an answer is to go back, to send something new to stay longer than 6 hours. The missing heat of Uranus is not just a curious anomaly, it is one of the central unsolved problems in planetary science. Two planets that formed in roughly the same part of the solar system, from roughly similar material, with roughly similar compositions, and one of them is glowing from within while the other is not. Understanding why could tell us something fundamental, not just about Uranus and Neptune, but about how planets in general form and evolve. And since ice giants appear to be extremely common among the planets found orbiting other stars in the galaxy, understanding our own two ice giants carries implications that reach far beyond our solar system. Astronomers studying exoplanets, planets around distant stars, have found that the most common type of planet detected so far, statistically, appears to fall in the size range of ice giants, not gas giants like Jupiter, not rocky terrestrials like Earth, something in between, something in the range of Uranus and Neptune, which means that Uranus, the planet we have visited exactly once, and for approximately 6 hours, the planet we do not fully understand, may actually represent one of the most abundant types of planets in the universe. We have one up close, we have been there once, and we don't yet understand it. Let that settle for a moment if you can, as you breathe slowly and the quiet settles around you. The most common planet type in the galaxy, and we know it mostly from one rushed afternoon in 1986. There is more. The cold, the tilt, the missing heat. These are real and confirmed, as strange as each one is. And they sit alongside each other in ways that make Uranus feel, as a world, genuinely unlike anything else we have encountered. A cold planet, slowly rolling through its orbit, each pole swinging through 42 years of light and 42 years of dark, carrying its tumbling magnetic field and its mysteries about warmth and interior structure, all while looking from a distance like a serene, nearly featureless pale blue sphere. The color, by the way, that soft cyan blue-green, comes from the methane in the upper atmosphere. Methane has the property of absorbing red and orange light while allowing blue and green wavelengths to pass through and reflect back. The result is that Uranus, when seen from space, appears wrapped in a cool, pale turquoise, peaceful, almost still. And that apparent stillness is itself a kind of illusion, because beyond the confirmed strangeness of the tilt, the polar nights, the missing heat, and the tumbling magnetic field, there are whole other dimensions of Uranus's nature that remain genuinely open, questions that are not settled by what Voyager measured, questions that cannot be answered without going back. We know, for instance, that Uranus has rings, 13 of them narrow and dark. Unlike Saturn's broad, bright, icy rings made of material ranging from dust to chunks the size of houses, Uranus's rings are thin, dark, and relatively unreflective. They were not discovered by Voyager. They were discovered in 1977, nearly a decade before the spacecraft arrived, by a team of astronomers, James Elliott, Edward Dunham, and Jessica Mink, who were watching Uranus pass in front of a distant star. The technique is called stellar occultation. As the planet passes between you and a bright star, the star winks out, and by timing exactly how long it takes and how the light fades, you can measure what is blocking it. On that night in 1977, the star blinked out several times before Uranus itself blocked it, and then blinked several times again on the other side. Rings. Narrow, dark rings orbiting the planet, each one causing the starlight to briefly dim as it passed between the star and the observers on Earth. 13 rings confirmed and catalogued. Some of them very narrow indeed, constrained in place by small moons called shepherd moons that orbit on either side of them and keep the ring particles from spreading. The whole ring system, invisible to the naked eye and dark enough to absorb most light rather than reflect it, wraps around the planet in the plane of its unusual equator, which means the rings, like everything else about Uranus, are oriented sideways relative to the rest of the solar system. From certain vantage points in space, Uranus's rings look like a bullseye, concentric circles viewed nearly face-on rather than the edge-on strips we see when looking at Saturn's rings from in the plane, which is beautiful in its own way. Another consequence of the tilt written into the very orientation of the debris field around the planet. And there are the moons. 28 of them now, with recent discoveries in 2023 adding to the count. All of them, every single one, named after characters from the works of William Shakespeare or the poet Alexander Pope. Miranda, Ariel, Umbriel, Titania, Oberon, Prospero, Caliban, Sycorax, Puck and Mab. A catalogue of literary characters orbiting an ice giant at the edge of the solar system, each name chosen not for planetary science reasons, but because of a naming convention adopted early on and carried forward ever since. There is something gently whimsical about that. A planet of rolling darkness and tumbling magnetism, and its moons are named for fairies and dukes and the characters of A Midsummer Night's Dream. Miranda, the smallest of the 5 major moons and the closest to Uranus, carries one of the most striking features in the solar system. It is a small world not much more than 470 kilometers across, which is tiny, smaller than many asteroids that get considerably more attention. And yet on its surface, Voyager 2's cameras captured images of Verona Rupes, a cliff face that rises by current estimates to somewhere around 20 kilometers. In comparison, Mount Everest, the tallest mountain on Earth measured from sea level, stands at about 8.8 kilometers. Verona Rupes, on a moon the size of a modest asteroid, is more than twice that height, possibly the tallest cliff in the solar system. How it formed is another open question. Miranda's surface is a peculiar patchwork of terrain types that look almost as though they don't entirely belong together. Smooth plains next to ancient cratered regions, next to chaotic, ridged terrain unlike anything nearby. One hypothesis is that Miranda was once catastrophically disrupted, broken apart by an impact or a tidal event, and then reassembled from its own debris, which is why different parts of it look so different from each other. Another is that some kind of ancient geological activity drove different materials to the surface in different places. Without more data, both ideas remain speculative. What is certain is that Verona Rupes exists, a cliff 20 kilometers tall on a world small enough that you could walk around it in a few weeks, if you could breathe there and had enough patience. It is the kind of detail that does not fit easily into any tidy narrative about what the solar system is supposed to look like. Uranus is full of those. The deeper interior, water, ammonia, and methane ices layered over a rocky core, is the reason scientists classify Uranus and Neptune as ice giants, rather than lumping them in with Jupiter and Saturn. The word ice here is a little misleading if you picture a snowball. At the temperatures and pressures inside Uranus's interior, these materials are not frozen in any familiar sense. They are dense, hot, pressurized fluids, more like a thick, electrically conducting slush than anything you might imagine when someone says ice. The pressures climb dramatically with depth, and it is those extreme pressures that give rise to one of the most evocative hypotheses in planetary science. The possibility, not proven but supported by laboratory experiments, that inside Uranus it rains diamonds. But that thread belongs to the next part of this journey tonight, where we'll follow it into the interior and then onward to the question of return. For now, let the confirmed strangeness of this place simply be. The 97.8-degree tilt, a planet on its side for billions of years, carrying the signature of a catastrophic ancient impact in the very orientation of its spin. The 42-year polar night's darkness so long it outlasts most of a human lifetime, unbroken night at one pole, while the other pole basks in 4 decades of continuous sun. The missing internal heat, a mystery that separates Uranus from its twin Neptune in a way that planetary science has not yet fully explained, leaving Uranus as the coldest planetary atmosphere ever recorded, negative 224 degrees Celsius, 49 degrees above absolute zero, colder than the farther, darker Neptune. The tumbling magnetosphere, the off-center magnetic field, the rings discovered by watching a star blink. None of this is a measurement error. None of it is an artifact of a bad flyby moment. This is Uranus confirmed as strange as advertised, and in some ways stranger, because the strangeness has been sitting in the data for nearly 4 decades, and we still don't have answers for much of it. There is something Uranus keeps doing in its quiet way as you read or drift or simply listen in the dark. It keeps gently refusing to be simple. Every time planetary science finds a framework, here is how giant planets form, here is how magnetospheres work, here is how ice giants retain their heat. Uranus sits somewhere slightly outside the framework, not dramatically rebellious, just quietly, not quite fitting. Like a word in a poem that is almost the right word, almost rhymes but not quite, and you keep returning to it. The scientists who study Uranus return to it too, decade after decade, with each new telescope observation, each new modeling effort, each reanalysis of the old Voyager data, including the 2024 reanalysis that started this whole conversation tonight. Jamie Jasinski and the team at NASA's Jet Propulsion Laboratory going back to magnetometer readings and plasma measurements from a spacecraft that flew past nearly 4 decades ago, and finding something new, something that reframes the mystery. That is how science works when it can't get more data. It mines the data it has more carefully, with new tools and new understanding, until the old measurements yield new answers. But there are limits to that approach. At some point there are questions that old data simply cannot answer, questions that require new measurements, new instruments, a spacecraft that can actually stay, can orbit, can sample the atmosphere directly, rather than flying past at tens of thousands of kilometers per hour. Questions that require going back. And we have not gone back. Not yet. We have been there once, briefly, in one unusual afternoon in January 1986. Voyager 2 took its measurements and continued onward, past Uranus, past Neptune 3 years later, and eventually out of the solar system entirely, into the interstellar space beyond the heliopause, where it travels still, carrying its 1970s instruments into the dark between the stars. Uranus has been waiting since then. The science suggests it will have to wait a bit longer, but not perhaps, impossibly, much longer. There are people working on it right now in offices at NASA and in university departments around the world. The question of when we go back and how and what we might find there, that is where this story goes next. For now, wherever you are, whatever time it is in your corner of the world, you know something real about this distant, pale cyan world. You know that it sits rolling on its side in the dark, with its 42-year nights and its missing warmth and its tumbling magnetic field, orbiting steadily at 19 times the distance from the Sun that Earth sits. It has been there for 4.5 billion years. The 42-year night at one pole is underway. The other pole is slowly emerging into light, and we have been there once. So let us go deeper then, into the planet itself, past that pale cyan surface, past the cloud decks of methane haze, down into the strangeness beneath. Because what Uranus is made of, on the inside, is one of the genuinely beautiful things about it. Not a mystery born of a bad timing flyby, not a textbook entry that may need revising. This is real and strange, and in its own quiet way, quite wonderful. We call it an ice giant. That name matters. You'll sometimes see Uranus lumped in with Jupiter and Saturn, the gas giants, those vast balloon worlds of hydrogen and helium, swirling and enormous. And Uranus is large, certainly. 4 times the diameter of Earth, roughly 14.5 times the mass. But it's made of something different, something denser and stranger than the airy outer layers of Jupiter or Saturn. The bulk of Uranus, as best we understand it from the data we have, is made of ices. And here the word ice can be a little misleading, so stay with me for just a moment. In planetary science, ice doesn't necessarily mean frozen solid at low temperature the way ice in your glass works. It means the right molecular ingredients: water, ammonia, methane. Under conditions of enormous pressure and temperature that exist inside a planet, under those conditions these molecules don't quite behave like anything you'd recognize. They're compressed, they're hot, they're somewhere between solid and fluid, and they make up the thick, dense middle layers of Uranus's interior. So imagine, if you can, layers. At the very center, a rocky core, not a soft gas, but something dense and solid, probably silicate rock and iron, maybe roughly the size of Earth in its own right, pressed hard under the weight of everything above it. Then wrapped around that core, this deep interior ocean of ices, water, ammonia, and methane, in proportions and states that we can only infer because no instrument has ever sampled them directly. They exist in that strange regime of high temperature and crushing pressure where the normal rules of how materials behave start to bend. And above that, a thick atmosphere mostly of hydrogen and helium with methane mixed in near the top. It's that methane at the top, the methane floating in the upper atmosphere, that gives Uranus its color. And this is one of the small, elegant facts about the planet. Methane absorbs red light. Red wavelengths of sunlight come down into the atmosphere, and the methane soaks them up. What bounces back out, what scatters back into space and into our telescopes, is the blue and the green end of the spectrum. And so Uranus appears to us as that soft, pale, washed-out cyan, a muted blue-green, the color of sea glass, on a cloudy morning. That color is not an illusion or a quirk of camera settings. It is a direct consequence of the chemistry of its air. And somewhere in that interior, in those layers of water, ammonia, and methane under pressures and temperatures we can barely imagine, something extraordinary might be happening. Or rather, something extraordinary might be raining. Diamonds. This is the part where you might reasonably think, surely this is a metaphor. Surely this is one of those scientists speculate lines that get stretched a little for drama. But it isn't quite. This is based on real laboratory work. In 2017, a team of researchers led by Dominic Krauss conducted experiments at the SLAC National Accelerator Laboratory using the LINEC Coherent Light Source, a facility that produces one of the most powerful X-ray lasers on Earth, to recreate the extreme pressure and temperature conditions of ice giant interiors. They took a material similar to what exists in the deep interior of Uranus, a hydrocarbon compound, polystyrene, as a methane stand-in. And then they slammed it with a shock wave of extraordinary intensity. Under those conditions, pressures millions of times greater than atmospheric pressure at Earth's surface, temperatures in the thousands of degrees, the carbon atoms in the methane-like compound separated from the hydrogen. The carbon atoms, under that crushing squeeze, reorganized themselves. They formed diamonds. Tiny, real diamonds detected forming in real time in the experiment, falling through a layer of hot, compressed hydrogen. Now, and this is important, the experiment demonstrated that the process can happen. It demonstrated the physics. What it cannot prove is exactly how it plays out inside Uranus, because there is no instrument inside Uranus to check. The diamond rain hypothesis is lab-supported, but the planet's interior is still inference. The conditions deep inside Uranus should, based on the 2017 Krauss experiments and the models, be consistent with carbon separating from hydrogen and sinking. Carbon is heavier, it would fall toward the center, and if it fell as diamond, perhaps tiny crystals, perhaps larger chunks building up over billions of years, there could be, somewhere in the deep interior of Uranus, a slow, perpetual rain of diamonds drifting down toward the rocky core. Sit with that for a moment. You're in your bed, or on your couch, or somewhere quiet and still, and there is a planet 19 times further from the sun than you are, in the dark right now, possibly raining diamonds. Not as a story. As physics, it's the kind of thought that is useful to carry into sleep. Something this strange being real. Now for a long time, and this is the other quiet thing worth unpacking, Uranus had a reputation for being slightly dull, the boring one, the plain blue marble, and it is worth talking about where that reputation came from, because it is not entirely fair, and it is, in part, another artifact of timing and instrumentation. When Voyager 2 passed by in January 1986, the images it returned showed something remarkably bland. Compared to Jupiter, with its swirling storms and its great red spot, its bands of cloud and color, its turbulent theatrics, Uranus looked almost featureless. A smooth, uniform pale blue sphere, barely a blemish on it. The cameras saw almost nothing, and so the narrative formed: Uranus, the boring ice giant. But here is the thing, when Voyager flew past, Uranus was near a solstice. The planet was oriented so that one of its poles was pointing roughly toward the sun and toward Voyager, which meant Voyager's cameras were looking more or less straight at the pole of a planet that, because of its extraordinary tilt and its pattern of seasonal circulation, happens to have relatively quiescent cloud patterns at the pole during solstice. It was a bit like photographing the top of someone's head and concluding they have no face. In the decades since, using the Hubble Space Telescope and ground-based observatories, including the Keck Observatory in Hawaii, astronomers have watched Uranus with much greater patience over longer periods as the planet has moved in its orbit and the sun's angle on it has changed. And what they've seen is quite different from that blank blue sphere. Storms, bright cloud features, bands of atmospheric activity, seasonal change as the planet's peculiar geometry shifts which hemisphere faces the sun. Uranus turned out to have weather. It turned out to have atmospheric dynamics that are interesting and complex and worth studying. The boring label was wrong. It was an accident of when we arrived. This matters because it adds to the picture we've been building tonight, the picture of a planet whose apparent character has been shaped at least partly by bad timing and limited snapshots. The blank sphere, the empty radiation belts, the apparently dead moons. One visit near a solstice during a rare solar wind squeeze. That's what we've been working from. It isn't nothing, but it isn't enough. Let's go back a little further though, because the story of Uranus doesn't start in 1986. It starts more than 2 centuries earlier on a night in March of 1781 in the English city of Bath. William Herschel was a musician by training, a German-born organist and composer who had moved to England, built a career in music, and then developed what can only be described as an extraordinary obsession with telescopes. He built his own, grindingly, patiently, polishing mirrors in his spare hours, making instruments better than almost anything commercially available at the time. And on the night of March 13, 1781, while systematically surveying the sky, he came across something that didn't quite look right. A small disk, faint, greenish, in a part of the sky where no star should have a disk. Stars, when you look through a telescope, are still just points. They are too far away to appear as anything but specks of light. But this object had a size to it. It extended. It was not a star. Herschel initially thought it might be a comet. That was the most sensible explanation. Comets can appear as fuzzy disks through a telescope. He reported it as such. But as other astronomers tracked it over the following months, watching its movement against the background of stars, it became clear that this was no comet. Its orbit was too circular, too orderly, too distant. It was moving in a nearly circular path around the Sun, far beyond Saturn, the outermost known planet at the time. This was something new, something that had never been classified before, a new planet, the seventh planet, the first ever discovered with a telescope. Every planet known before, Mercury, Venus, Mars, Jupiter, Saturn, had been known since antiquity, visible to the naked eye, noticed by observers thousands of years before telescopes existed. Uranus was the first that required an instrument to find. Herschel had, in an ordinary evening of methodical observation, doubled the known size of the solar system. Now he got to propose a name. And he chose, perhaps predictably, for someone whose career had been built under the patronage of the British Crown. Georgium Sidus, the Georgian star, named for King George III, who was at the time the reigning British monarch. It was, in hindsight, a bold choice. Patriotic, certainly. Not universally beloved by astronomers elsewhere in Europe, who did not feel particularly inclined to name a planet after the British king. The name that eventually stuck came from someone else. Johann Bode, a German astronomer, proposed naming it Uranus, after the ancient Greek god of the sky, the primordial deity from whom Saturn, Cronus, was descended in mythology. It fit the naming convention. All the other planets were named for Roman gods from the same mythological family: Jupiter, Saturn, Mars, Venus. Uranus sat above them all in the ancient cosmology. The name made sense. And gradually, over decades, Bode's suggestion won out, and the Georgian star became Uranus, and that is what it has been ever since. There is something quietly funny about the history of this name. Herschel discovered the planet and wanted to name it after a king. The astronomers of Europe, more attached to mythological convention than to British politics, chose a Greek sky god instead. And the word they chose happens to have developed in the modern English-speaking world an association with juvenile humor that none of the 18th century astronomers could possibly have anticipated. Herschel might have had the last laugh in a sense if he'd known, but whatever you call it, the planet was there. It had always been there. There are records of earlier astronomers, including John Flamsteed in 1690, who had observed it and catalogued it as a star, saw it, recorded it, and moved on, not realizing what they were looking at. Uranus had been watched by human eyes for at least 90 years before Herschel understood it. It just looked, through early instruments and without careful tracking, like a dim, unremarkable star. The solar system's seventh planet, hiding in plain sight. And then there are the rings. Because Uranus does have rings, 13 of them as far as we know, narrow, dark, relatively hard to see. Not the grand spectacular curtains of Saturn with their gleaming ice and their cathedral window sweep across hundreds of thousands of kilometers. Uranus's rings are thin and dark and subtle, more like pencil marks than broad brushstrokes. But they are real, and they were found before any spacecraft ever got there, which is itself a small story worth telling. In March of 1977, a team of astronomers, James Elliott, Edward Dunham, and Jessica Mink, were observing Uranus as the planet was about to pass in front of a distant star. This is a technique called stellar occultation. As the planet crosses the line of sight to a star, the star blinks out. You can measure how long and how cleanly it blinks out to learn about the planet's atmosphere, its size, its shape, standard planetary science. But what Elliott, Dunham, and Mink noticed was that the star didn't just blink out once when Uranus blocked it. It flickered. Before the planet reached the starlight dipped and recovered several times in sequence, and then, after the planet had passed, it dipped and recovered again in the same symmetric pattern. Something around Uranus on both sides was blocking the starlight. Something narrow and dark encircling the planet, rings, discovered not by going there, not by imaging, but by watching a star blink in a pattern and working out what the pattern meant. It was an elegant piece of science, the detection of something in the solar system by its shadow before anyone had ever seen it directly. Voyager 2 would confirm the rings when it arrived in 1986, photographing them directly and giving us our first images of these dark, narrow bands. 13 of them made of dark material, likely carbon-rich compounds, much darker than Saturn's bright, icy rings, which is part of why Uranus's rings weren't spotted until a lucky occultation observation in 1977. And then there are the moons, 28 of them in the most current count. And the moon count has been growing as newer observations and reanalyses turn up smaller, fainter members of the family. Uranus's moons have something that makes them unlike any other collection of moons in the solar system. They are all named after characters from the works of William Shakespeare and Alexander Pope. Miranda, Ariel, Umbriel, Titania, Oberon, Puck, Caliban, Prospero, Sycorax. The names read like a cast list from a theatrical evening, which in a sense is what they are, a literary solar system orbiting a sideways planet. The 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are the ones Voyager 2 managed to photograph on its flyby. Titania is the largest, at about 1,580 kilometers across. Oberon is close behind. Ariel and Umbriel are a matching pair. And then there is Miranda. Miranda is the smallest of the 5 major moons, and it is in some ways the most extraordinary. It is a strange object, scarred and fractured and seemingly jumbled, its surface a chaotic patchwork of different types of terrain, old cratered plains rubbing up against younger, more angular terrain of ridges and canyons. There are models suggesting Miranda may have experienced some catastrophic breakup or restructuring in its past, though the details remain genuinely unclear. But the feature that makes Miranda genuinely remarkable, the thing that stopped people in their tracks when Voyager's photographs came back, is a cliff, Verona Rupes, named in keeping with the Shakespeare theme after the city in Romeo and Juliet. A cliff face, a scarp that drops in some estimates up to approximately 20 kilometers. 20 kilometers of sheer vertical drop from the top of a cliff to the ground below. To put that in proportion, Mount Everest, measured from its base, rises roughly 8.5 kilometers. Verona Rupes, by comparison, is thought to be more than twice that height in sheer vertical face. It is, depending on how you define the measurement and which part of the surface you're comparing it to, one of the tallest known cliffs in the entire solar system. and it is orbiting a sideways planet 2.5 billion kilometers away from where you're lying right now. There is a small, pleasant thought buried in the astronomy of Uranus's moons. The thought that somewhere in the dark, a moon named Miranda has a cliff named after Verona, and everything about that is both absurd and quietly poetic. Human beings over centuries gave names to the moons of a planet they had barely seen, borrowing from Shakespeare and from Pope, and one of those names ended up labeling the edge of one of the most dramatic geological features anywhere in the solar system. Now, we have been here for a while tonight. We've gone from that astonishing 2024 reanalysis through the magnetosphere and the tumbling field and the missing heat, through the tilt and the polar nights. And now we've walked through the interior, the ices, the core, the possibility of diamonds, and the rings and the moons and the history. Herschel and Bode, the Georgian star. Elliot, Dunham and Mink watching a star blink. And the question that has been waiting quietly underneath all of this, the question that the whole story has been circling around, is when do we go back? Because that's where everything leads. That's the place the whole narrative of Uranus points to. We've been there once. We're not sure what we saw was typical. The planet is stranger than we fully understand, and we have theories about why, and some of those theories are well supported and some of them are not. And the only way to find out is to send something that can stay, not a flyby, not 6 hours of close data at tens of thousands of kilometers per hour, an orbiter, a probe that goes into the atmosphere directly, something that can take its time. The name for the mission that would do this is the Uranus Orbiter and Probe, the UOP. And here is the thing about it. It is not a dream exactly. It is not a speculative future aspiration that scientists mention with a vague hope it might someday happen. It has been formally named the highest priority flagship planetary science mission for the coming decade by the most authoritative body that makes such recommendations. The 2023 Planetary Science and Astrobiology Decadal Survey, published by the National Academies of Sciences, Engineering and Medicine, the report that the scientific community produces roughly every 10 years to tell NASA where it should focus its major efforts, placed the Uranus Orbiter and Probe at the top of the list, not second, not tied for first. First, the number one flagship mission priority for planetary science in the decade following the survey. That is a statement of community consensus. It means that the people who study planets for a living, who have access to everything we know about every world in the solar system, looked at all of it and said, Uranus is where we need to go. Uranus is the most important destination we haven't properly explored. The case for going is stronger than the case for anything else on the list. And the reason the community reached that conclusion is precisely the accumulated strangeness we've been talking about tonight. The unexplained missing heat, the anomalous magnetic field unlike anything else in the solar system, the unanswered questions about the moons and whether they harbor subsurface oceans or geological activity, the tilted, compressed, possibly non-representative magnetosphere from the 1986 Flyby. The need to understand ice giants as a class of planet, because ice giants, it turns out, appear to be extremely common in the galaxy. When astronomers observe other planetary systems, ice giant-sized worlds show up frequently, and we have 2 of them in our own solar system, and we understand them poorly. Understanding Uranus and Neptune would help us understand an enormous category of worlds that appear throughout the universe. So there is scope here beyond one strange, tilted planet. Going to Uranus is, in a sense, going to learn about a kind of world that might be among the most abundant in the cosmos. Now, and this matters because it is part of the beauty and the frustration of planetary exploration, getting there is not a simple matter of deciding to go. The distances involved are humbling. Uranus sits roughly 19 times further from the Sun than Earth does. Light takes about 2.5 hours to travel from the Sun to Uranus. A spacecraft, even a fast one, cannot manage light speed. Voyager 2, moving at its extraordinary velocity, took about 4.5 years to reach Uranus after launch. A mission designed with more mass, more instruments, more fuel for orbital insertion, designed to slow down and enter orbit rather than just fly past, will take longer. Current mission planning estimates for a Uranus orbiter and probe suggest a journey of somewhere in the range of 13 years or more, depending on the exact trajectory. That means the journey to Uranus is not measured in months or even in a few years. It is measured in more than a decade. A spacecraft launched in the early 2030s might arrive in the mid to late 2040s. The scientists who are right now in their 30s, working on the mission concept, planning the instruments, arguing over the trajectory, writing the papers, some of them may be retiring by the time their spacecraft reaches its destination, and the trajectory itself matters enormously. The solar system is not just a collection of targets sitting patiently at fixed distances. It is a clockwork of orbits and alignments, and the positions of the planets relative to each other create windows, opportunities where you can use a planet's gravity to slingshot a spacecraft outward, gaining speed without burning more fuel. These are called gravity assists, and for a mission to Uranus, the most favorable of these windows involves Jupiter. A spacecraft launched at the right moment can swing past Jupiter and receive a gravitational nudge that shortens the journey significantly. The mission planners have identified the early 2030s as offering favorable Jupiter gravity assist launch windows. A launch around 2031 or 2032 aligned to swing past Jupiter could get a spacecraft to Uranus in a reasonable, though still very long, time. Miss that window and you're waiting for the next favorable alignment. The planets don't pause for budget cycles. This is one of those places where the pace of planetary science makes you feel the scale of it. A decadal survey recommendation in 2022 and 2023 pointing to a launch window in the early 2030s, pointing to an arrival somewhere in the 2040s, each step a decade apart. The decisions being made now will unfold over spans of time that dwarf any individual career, any election cycle, any human institution's comfortable planning horizon. And yet people keep doing it. They keep making the case, writing the papers, designing the instruments, because they understand that the return on investment is real and enormous. That when a spacecraft finally settles into orbit around Uranus, begins sampling the magnetic field over dozens of orbits rather than a few hours, drops a probe into the atmosphere to measure its composition and structure directly, watches the moons up close over months and years. What comes back will rewrite our understanding of a whole category of planet in a way that ripples outward to our understanding of planetary systems everywhere. The answers to the questions we've spent this night on: why does Uranus emit almost no internal heat while Neptune glows? Is the tumbling magnetic field actually how it always looks, or did we catch it in a strange moment? Are Miranda and Ariel and Titania geologically alive, with subsurface water or activity we couldn't detect from a passing glimpse? What does the normal Uranus magnetosphere look like without a solar wind squeeze compressing it? What does its atmosphere actually contain when you go deeper than a telescope can reach? All of those answers are locked inside a world we visited for 6 hours. 6 hours, and then silence. And then, from the silence, the astonishing work of scientists like Jamie Jasinski and the team at JPL, sitting with 40-year-old data, reading it with new understanding, and finding in it the quiet revelation. We may have been looking at a flinch, a compressed, unusual, transient state of a planet that has spent 4.5 billion years doing whatever it normally does, and we happened to arrive on one of the 4% of days when the solar wind had squeezed it into something abnormal. That is, if you step back from it, one of the more remarkable things about human science. The data Voyager 2 collected in January of 1986 was stored, studied, published, and then archived. And in 2024, someone looked at it again with better models and sharper questions and found something that changes the interpretation of almost everything the Flyby told us, not by going back, not with new instruments, by sitting with old recordings and thinking harder about what they meant. That's the thing about knowledge, and it doesn't always come from new expeditions. Sometimes it comes from reading the old ones differently. But eventually the old readings run out. Eventually you do need to go back. And the case for going back to Uranus is, in 2024 and beyond, the strongest it has ever been. Not just because of the decadal survey priority, but because of what the 2024 reanalysis revealed, that we know less than we thought we did. That the textbook entry for Uranus, which already had the distinction of being built on one afternoon of data, may need to be revised in its most basic claims about what the planet's environment normally looks like. We have, in a sense, been given more uncertainty as a gift, more reason to go, more questions that can only be answered by going. And so somewhere in the planning offices and university departments and NASA centers, the work continues, slowly, methodically, the way science always moves, but continues. Instruments are being designed, trajectories are being optimized, arguments are being made and written down and reviewed and revised. A mission to Uranus is not yet real in the sense of having a launch date, a confirmed budget, a rocket assigned, but it has the community's highest endorsement. It has the window in the early 2030s that makes it physically possible to do in reasonable time. It has a scientific case that strengthens every time someone like Jasinski opens the old data and finds something new in it. Uranus will keep rolling. It will keep rolling on its side through the dark, as it always has, its pole tipped toward or away from the sun in those long, slow seasons of 42-year light and 42-year night. The magnetic field will keep tumbling in its chaotic way, connecting and disconnecting with the solar wind in its odd, asymmetric fashion every 17.5 hours. Whatever is happening in the deep interior, the ices under pressure, the possible slow sift of carbon toward the center, will keep happening as it has for billions of years, indifferent to our schedules and our budget cycles. And the rings will keep turning quietly. 13 dark, narrow bands found by 3 astronomers watching a star blink on a night in 1977 in one of the small, elegant moments of planetary science that nobody talks about enough. And Miranda will keep its cliff. Verona Rupes dropping 20 kilometers into the fractured landscape of a small, strange moon named for a city in a play written by a man who died 165 years before Uranus was even discovered to be a planet, and 360 years before anyone photographed the cliff. These are the things that exist out there, whether we're watching or not, and we have been there once. Let that settle for a moment. One visit. One strange, brief, compressed day in January 1986. And from those few hours of data, those magnetometer readings and plasma measurements and camera frames and infrared spectra, came nearly everything we know in detail about the 7th planet, the radiation belts that may not be typical, the moons that might be more active than we thought, the tumbling magnetosphere, the missing heat, the bland near-solstice sphere that later turned out to have weather. All of it, one afternoon. It makes you think about how much of what we call knowledge is really a single snapshot taken at a particular angle, in a particular light, at a particular moment. How much of what we know about anything rests on a handful of encounters, interpreted as best we could at the time, waiting for someone to look again and see something different. There is something comforting in that if you sit with it, because it means the universe is larger than our current picture of it. It means Uranus, which sounds thoroughly charted in the textbooks, is still genuinely mysterious. The magnetosphere we didn't understand in the old way might make more sense in the new way, and the version of the planet we haven't seen yet might be stranger still. The moons we dismissed might have something to say. The universe has not been fully explained. It keeps offering new readings of old recordings, new questions under old answers. There is more to find out. There always is. And you, wherever you are right now, whatever small corner of the night you're in, you are made of the same elements as Uranus. The water in your body, the carbon in your bones, the oxygen in the air you're slowly breathing in the quiet of wherever you are. The universe assembled all of it, including you, from the same early inventory of atoms. The ices of Uranus and the molecules in your cells share the same origin. You are not separate from the solar system. You are a part of it, a dense, particular, temporary part of it, breathing slowly in a bed on the third planet from a star. Uranus is 19 times further from that star than you are. It has been rolling on its side for 4.5 billion years. Its polar night is quietly proceeding. Its diamonds, if they exist, are sifting slowly downward toward a rocky core no instrument has ever touched. And the first spacecraft will take 13 or more years just to get there. Back at the start of tonight, I asked where you were listening from. I asked what time it was in your corner of the world. And wherever that is, whether it's very late or early, or somewhere in the quiet middle hours, you've spent this time with one of the strangest places in the solar system, a place we almost certainly don't fully understand yet, a place that may spend the next 20 years surprising us as the mission concept becomes a real spacecraft on a real trajectory through real space, closing the distance 1 year at a time. If you enjoyed drifting through all of this tonight, the one strange day, the compression, the missing heat, the sideways tilt, the diamonds and the cliff, and the blinking star, and William Herschel naming a planet after a king, then a gentle like and a subscribe really do help. Small creators like me rely on your support to keep making these slow journeys into the dark. I'm genuinely grateful for the time you've given this tonight. And if you want to leave a note telling me where you are and what time it is in your corner of the world, I would love to know. Every answer to that question is its own small wonder. But for now, let the thought of Uranus settle in, somewhere under everything else. That pale cyan world, rolling steadily through the dark at 19 astronomical units, with its 42-year nights, and its tumbling field, and its one afternoon of company in 1986, before the spacecraft moved on. It's still out there. Good night from up here in orbit. I'll keep watch while you drift.